Module 15D, we're going to start looking at the integrated rate laws. You are responsible for knowing the reactions for zero order, first order, and second order, and being able to graphically identify if a reaction is zero, first, or second order. With these equations, you should be able to determine the concentration of a reactant or product at any time after reaction has started, as long as you know if it's zero, first, or second order. You should be able to calculate the time required for a given fraction of sample to react, and the time required for reactant concentration to reach a certain level. You need to know how the integrated rate laws can be used graphically to determine the order of reaction, and understand and correctly apply the concept of these integrated rate laws to half-life equations. Deriving the rate law for reaction from experimental data as well. We will not be integrating these. That is calculus. That is, you can do that in your math classes, but we will be using the integrated versions of these equations. So integrated rate laws. Let's suppose that I have a reactant A going to products, and this is first order. The definition of rate is equal to the negative change in concentration of A over change in time. The rate law for this reaction would be rate equals K, my rate constant, times the concentration of A. I equate this where the negative delta change in concentration of A at time t over A naught, meaning initial concentration, is equal to negative KT. So AT here is A at any time, at concentration of A at a specific time, and this is concentration of A initially. That little zero means initial, or not. We say it like KNOT not. We're going to integrate this. When we integrate it, we get your integrated rate law. The natural log of the concentration of A at any time divided by the concentration of A initial is equal to negative KT. This is our first order integrated rate law, where this change in concentration of A over change at some specific time, whatever given time you're looking at, divided by the concentration of A naught represents the fraction of A remaining at time t. You can use this to solve for time. We can say how long. How long until 30% of the sample has reacted? How long until only 40% of the sample remains? If it's run for 45 seconds, how much remains? We can answer those questions with this equation. This equation can also be rewritten as the natural log of A sub t is equal to negative KT plus natural log of A sub O. The advantage to this is written in the y equals mx plus b form, or the linear form that we often graph it in. So you can remember the reaction either way, I do not care. This, or both, or know how to convert between the two. But you're going to be using both forms of this reaction for zero order, first order, and second order rate laws. For a first order reaction, a plot of the natural log of the concentration of A versus time results in a straight line where the slope is negative K. If I just plot the concentration of A as a function of time, I see that it is not a linear plot. First order means that the rate of reaction is dependent upon the concentration of the reactant. It is a 1-to-1 ratio there, right? As the concentration is doubled, the rate doubles. As the concentration is half, the rate halves. Well, what's happening in a reaction? In a reaction, of course, we know that the concentration is decreasing as I go along. The concentration of A initially is much higher than the concentration, say, 5 minutes in. When the concentration is decreased like that, the rate of collisions, of successful collisions for the reaction to actually go forward, has been decreased. Therefore, it's going to have a slower rate. So if I just looked at the concentration of A over time, I would have a nonlinear plot like this. But if I plot it based on that equation for first order, natural log of A sub t equals negative KT plus the natural log of A naught, I get a linear line. So if I plot data where I take the natural log of the concentration of A at time t, and I plot that as a function of time, and it gives me a straight line, first of all, I know the slope equals negative KT, but I also know then that this data represents a first order reaction. So why do I care? Because I can solve for time. This is a very important consequence of these reactions. I can actually solve for time. I can say how much time passes before 50% of the sample's been reacted. How much time until I have 75% remaining. How much time until only 10% remains and it's now safe to dump this chemical. If I have to buy a chemical that's radioactive to use for a reaction, how much time do I need to buy ahead of time? How much time do I need to account for a half-life of a reactant that's going to start to decompose, and I need to take that into account when I do my calculations. I can solve for time. Half-life of a first-order reaction, T to the 1/2, is the time required for half of that substance to react. Half-life comes into play when we talk about nuclear chemistry, but it also comes into play in things like medicine. It's a really important concept for us to understand, and kinetics are the way we get there. So let's walk through this derivation. First order, we know the rate law is equal to is the rate equals K times concentration of A. We're still looking at this reaction of A going to products. So if I wrote the rate law for this, I would write rate equals K times concentration of A. The integrated rate law we have the two forms of it, but the more conveniently used form for this time, when you're not graphing at least, when you're solving for time, is the natural log of A at time t over A initial. So concentration of A at some specific time divided by the concentration of A initially is equal to negative KT. From the definition, T is equal to T to the 1/2. I want to know the half-life, so time at 1/2. So T to the 1/2, T equals T to the 1/2 when the concentration of A at time T is equal to 1/2 the concentration of A initially. I want to know how much is left after half the sample has been decomposed. That means the concentration has also been halved. Natural log of 1/2 A naught over A naught. So all I've done here is substituted this in for AT into this equation. This equals negative KT to the 1/2. So instead of just writing T, I'm writing T to the 1/2 for my T. Simplify this equation. Natural log of 1/2 is equal to negative KT to the 1/2. The natural log of 1/2, I can say natural log of 2 is equal to positive KT to the 1/2, log rules here, basically multiplying through by -1 throughout the entire reaction. And from there, I get T to the 1/2 equals the natural log of 2 over K. And you will often see this written as T to the 1/2 is equal to 0.693, which is just the numerical value of natural log of 2 over K. This is the half-life equation for first order reaction when you're looking the half-life equation if you have a first order kinetic reaction. Do note here that the half-life of first order reaction is completely independent of your initial concentrations. What I see here, T to the 1/2 is just dependent upon the rate constant. Doesn't have concentration in here, just your rate constant. That's going to tell me how long it's going to take for it to decompose. So first order reactions. First order integrated rate law, again, natural log of AT equals negative KT plus natural log of A naught. You will also see this written in the other form, natural log AT over A naught equals negative KT. You need to understand how to derive or how to flip back and forth between these two because you're going to be using both of them all the time. I would memorize one and understand the log rules to flip to the other. If I plot the natural log of the concentration of A versus T, I will get a straight line. That is if this is first order. With respect to reactant A. The T to the 1/2 equation is 0.693 divided by K, your rate constant. It is independent of concentration. Basically what that means is it doesn't matter how much I have, at a certain time, half of it will decompose. So, if the half-life is 10 minutes, after 10 minutes, half will decompose. After 20 minutes, another half will decompose. After 30 minutes, another half will decompose. And when I say another half, I mean half of what's remaining. So if you have a sample, 10 minutes, 50% has decomposed. 10 minutes later, 50% of that has decomposed. 10 minutes later, 50% of that has decomposed. 10 minutes later, 50% of that. And it keeps going. It's not that it disappears, it's just that it eventually gets to the point where there's very little left. The half-life is defined as the time it takes for a reactant concentration to reach half of its original concentration, and first-order half-life does not depend on concentration, completely independent. So we see here, if I take the natural log of N2O5 versus time, I get a straight line here. That means that this reaction is first order. With respect to N2O5. The previous module, we talked about using initial rates to determine the order of reaction. In this section, we're using integrated rate laws to determine the order of reaction. Half-life of first order reaction, let's say again, at time equals 0. If the concentration was 1 molar, after 1 half-life, I would have 0.5. After 2 half-lives, 0.25. After 3 half-lives, 0.125, etc. It's not, again, that the sample ever actually completely is gone. It's that half of the sample breaks down every half-life. So however long that half-life is, we're losing half of it every time we have another integration. Radioactive decay. So the half-life of iodine-131 is 8 days. That means after 8 days, half the sample has been has decomposed or broken down. Half the sample is no longer radioactive. After another 8 days, so after 16 days, we see we're down to 1/4 of the original concentration. After 24 days, an additional 8 days, we're down to 1/8 of the original concentration. After 32 days, we're down to 1/16 of the original concentration. That's what I mean by that half-life and half of it decomposing. Half of it is no longer radioactive after each time. You will talk about nuclear chemistry and radioactivity and what causes this and how it undergoes decay closer to the end of the semester. But for now, just know that this is what's happening. These equations will come back and you'll understand how the nuclei themselves are able to undergo this decomposition or decay, radioactive decay, to stabilize themselves more. But for now, you need to understand the kinetics of it. So let's work 2 examples. The reaction A going to products has been experimentally determined to be first order. That is important. If the rate constant for this reaction is 0.0462 minutes to the -1 at a certain temperature, how long would it take for 90% of A to react? Well, we're talking here about a reaction of A going to products. If I wrote the rate law here, how do I know it's A going to products? Because it told me so. If I wrote the rate law here, I would write rate is equal to K times A. Again, there's a little invisible 1 up there, but we don't usually write that. It tells me it's first order, so I know the equation I need to use is the natural log concentration of A at time t divided by concentration of A initial is equal to negative KT. I'm trying to find time when 90% of it has reacted. If 90% has reacted, that means 10% is left. I'm going to say natural log of 0.100 is equal to negative 0.0462 minutes to the -1 times t. What is this though? Where did I get this number? That represents 90% of A has reacted. That represents 10% remains. That's the ratio of how much remains to how much I had originally. You could also write it as 10 over 100 and plug that into there. So the natural log of 10 over 100. Because 90% of A has reacted, that means at time t, 10% remains. I just did the math, and instead of putting 10 over 100 in the log, I just did 0.1. But you need to recognize that that means 90% reacted, 10% remains. You solve this out. So again, you could also write this as natural log of 10 over 100 equals negative 0.0462 minutes to the minus 1 times t. They mean the exact same thing. And when you solve for t, you find this to be 49.8 minutes. I have 3 sig figs, so I have 3 sig figs here. I didn't write the 3 sig figs in here. It would be 0.0 in decimal place there. But it is 3 sig figs. So I have 3 sig figs here and 3 sig figs here. So 3 sig figs, and my final answer here, time is equal to 49.8 minutes. So how long would it take for 90% of A to react? Almost 50 minutes. But that's using that equation. How about this other example? If the half-life of a certain first-order reaction is 15 minutes, how long would it take for 67.5% of this reactant to react? So again, I know A naught is my starting concentration. I know A over T divided by A naught is equal to the fraction of A remaining at time t. I'm telling you that the half-life is 15 minutes, and I want to know how long it would take for 67.5% of the reactant to react. Definitely needs to be less than 15 minutes, right? So let's see. T to the 1/2, 15.0 minutes. I'm going to use that information to find K. So number 1, use T to the 1/2 is equal to natural log of 2 divided by K, or you can say 0.693 divided by K, I don't care which one you do, to find K. I need the rate constant. I don't have it, but I need to complete this calculation. Then I'm going to use my equation, natural log of AT over A naught equals negative KT, to find how long it's actually going to take. So number 1, K is equal to natural log of 2 over T to the 1/2. Just rearrange that equation. This is equal to 0.693 divided by 15.0 minutes. I find my rate constant to be 0.0462 minutes to the minus 1. Now I'm going to plug this into my equation. I'm going to say the natural log, 0.325. Why 0.325? Because 67.5% has reacted. So I can either say 32.5 over 100, or I can just do the math ahead of time, which is what I did. But it's how much is remaining, not how much is reacted, how much remains. 32.5% remains, which is 0.325 of the original sample, equals negative 0.0462 minutes to the minus 1 times T, and I get a time of 2.43 minutes. What if your reaction is second order? We know that if A goes to products, second order means that if I double the concentration of A, the rate quadruples. We write this as the rate is equal to K times A quantity squared. The second order rate law equation is integrated rate law is here. 1 over the concentration of A at time t is equal to KT plus 1 over A naught. This is again in the form y equals mx plus b, because that is useful to us. Second order, if I just plotted the concentration of that reactant versus time, I see a steeper slope than I did when we looked at first order, which makes sense, right? Because if I double the concentration, the rate quadruples. That means when it's reacting, it's going to react at a faster rate. If I take the reciprocal of this line, though, I get a straight line, and it's the slope. So if I take 1 divided by the concentration, and I see a straight line, I know that reaction is second order. I can actually plot this experimentally. I can run a reaction, plot the concentration of a reactant over time, plot it, and when I see the inverse of it, giving me a straight line against time, I know it's second order. So 1 over a versus time is a straight line where the slope is equal to k. T to the 1/2 for a second order reaction is equal to 1 divided by k times a naught. Second order T to the 1/2 does depend on concentration. We can see the concentration in the expression. So you are responsible for both of these equations. We also have zero order integrated rate law. You need to know this equation. You need to know this equation. The plot of the concentration of A versus time gets to a straight line. What does zero order mean? Zero order means A going to product, where if I double the rate of A, or if I double the concentration of A, the rate remains unchanged. If I half the concentration of A, the rate remains unchanged. If I quadruple the rate of A, the concentration remains unchanged. The rate law here, rate is just equal to k. This again in the form y equals mx plus b, because this is useful to us if I try to plot this data. If I plot the concentration of A versus time and I get a straight line, I know it is zero order. And where the slope is equal to negative k, and you can see your half-life equation for a zero order reaction. T to the 1/2 also depends on concentration here, where T to the 1/2 is equal to the initial concentration of A divided by 2 times your rate constant. An overall summary slide of your integrated rate laws. Zero order, meaning A going to product. This means zero order means that it's completely independent of concentration of A. So if I take the concentration of A and multiply it by 2, rate is unchanged. We write this as rate is equal to k, and the equations you need to know are here and here. If I plot the concentration of A versus time, I get a straight line where the slope equals negative k. First order means if I double the concentration of A, the rate also doubles. I write this as rate is equal to k times concentration in A. The equations you need to know, here and here. And if I plot the natural log of the concentration of A versus time, the slope equals negative k here as well. And second order, A going to product. Second order means that if I double the concentration of A, that the rate is quadrupled. We write the rate law as, that should not be negative right there. I didn't catch that. Rate is equal to k times concentration of A. The equations you need to know, here and here. And please make sure that you make note on your slide that is rate is equal to k times concentration of A squared. There should be no negative in front of there. I apologize. But if you plot the reciprocal of the concentration versus time, you see the slope is positive and equal to k. One of these will give you a straight line. So let's work a couple examples. The reactant A going to products. Second order in A. When the initial concentration of A is 0.100 molar, the reaction is 20% complete in 40 minutes at 50 degrees C. What is the half-life of this reaction? So I know it's second order. T to the 1/2 for second order is equal to 1 over k times the concentration of A naught. I'm trying to find that half-life. In order to solve this, though, I need to know what k is. I know what the initial concentration is, but I don't know what k is. So how can I find k? Well, what's my other equation? 1 over concentration A at some time t is equal to KT plus 1 over concentration of A naught. Plug in what we do know. We know that after 20% completion, and 20% completion takes 40 minutes. 20% completion means how much remains? 80% remains. I started with a 0.1 molar solution, so if 80% remains, I must have 0.0800 molar. Trying to solve for K. And my initial concentration is 0.100 molar. I'm going to simplify this. Doing the division, I get 12.5 minus 10.0 is equal to KT. I do know what T is. It tells me 40 minutes. I'm just trying to not plug in any numbers until I have to. So 12.5 divided by 10, 2.5. Let's divide this by time now. 40 minutes. This equals K. I get a K value of 0.062. My sig figs are right here, but I'm going to carry an extra number right now just to be safe. Minutes to the minus 1. So my K value, my rate constant, is 0.062 or 0.063 minutes to minus 1. Again, I'm just writing 0.0625 so that I don't create round off error when I do the calculation. Haven't quite answered the question though. What I really need is t to the 1/2. So now I'm going to plug that information into this equation. T to the 1/2 equal to 1 over 0.0625 minutes to the minus 1 times my initial concentration of A, which is 0.100. I get t to the 1/2, solve that through, and I find it to be 160. I do need just 2 sig figs here, because my sig figs are here. 160 minutes. So, what's the half-life of this reaction? 160 minutes. What about this example? A reaction A going to products is found to be second order with a rate constant of 2.5 times 10 to the negative third molar per second at 35 degrees C. Let me check. This is actually molar per second. Dropping units over here. I apologize. There. That's the correct units to keep them through. 35 degrees C. If the initial concentration of A is 2.95 molar, what will the concentration be after 20 seconds? So again, I know that I've got 2 equations for second order reactions. I want to know concentration after 20 seconds. So I'm going to plug in 1 over concentration of A at time t, what I'm trying to find, is equal to my rate constant, 2.55 times 10 to the minus third, molar to the minus 1, second to the minus 1, times time, 20 seconds, plus 1 over A initial, and A initial is 2.95 molar. I'm running out of room. 1 over AT. I'm going to do the multiplication here first. 0.051 molar to the minus 1. And the division here. 0.3389 molar to the minus 1. Combine these together, this gives me 0.3899 molar to the minus 1, and that is equal to 1 over T. 1 over A sub T. Solve for A sub T. So just to write these back together, 1 over A sub T is equal to 1 divided by 0.3889 molar to the minus 1. This gives me a value of A sub T equal to 2.56 molar. So after 20 seconds, if the rate constant of this reaction is 2.55 times 10 to the minus third molar, and this is a second order reaction, If the initial concentration was 2.95 molar, after 20 seconds, I will have 2.56 molar remaining. How can I determine the rate law? Well, I do have to determine order experimentally, right? The concentration of A, I can do this by initial rate, or I can do it as a function of time. So initial rate is what we talked about in the previous module, where we compare the initial rates of different reactions. As we change the concentration of A, we can determine if it's zero order, first order, second order, etc. I can also determine this as a function of time. For this you can do this graphically. And you need to know those three equations for zero order, first order, and second order. We can qualitatively analyze this and monitor concentration of changes over time. If you are doing it, initial rate, again, was the previous module. As a function of time is your integrated rate laws. You need to ask yourself which line is linear. If you can plot the concentration of A versus time, and it is linear, this is zero order with respect to A. K is equal to the negative slope of that line. The rate is written as K. I say K to the concentration of A of 0. Really rewrite this as rate equals K. If you plot the natural log of A versus time, this is considered first order with respect to A. K is the negative slope of that line, and we write this as rate is equal to K times the concentration of A. If you plot the inverse of A, so 1 divided by A versus time, and it's a straight line, this is considered second order with respect to A, where K, not negative, but K is the slope of that line, and the rate law is written as rate equals K times A squared. Here's an example of how this actually looks with some experimental data. Crystal violet is a common dye that we use to show students what a first order reaction would look like. What we do is we take this dye and we react it with sodium hydroxide. The sodium hydroxide disrupts the conjugation of the bonds and therefore destroys the color of the compound. It's no longer purple. We see here in the graphs we have time, absorbance. This is absorbance of crystal violet. We've got crystal violet concentration, the natural log of the crystal violet concentration of 1 over crystal violet concentration. We then graph three things. We graph the time versus crystal violet. We graph time versus the natural log of the crystal violet concentration. And we graph time versus 1 over, or the reciprocal of the crystal violet concentration. The absorbance is what we've measured, and we use Beer's law to determine the concentration. We plot all three of these. Crystal violet concentration versus time. That line is not linear. The natural log of crystal violet concentration versus time, we see a linear plot, and the reciprocal of the concentration of crystal violet as a function of time, we see that line is not linear either. We compare these three graphs, we see this one is linear. Therefore, we can say this reaction is first order with respect to crystal violet. So integrated rate laws, you need to know those three equations, but you also need to recognize graphically how can you tell quickly if a reaction is zero order, first order, second order. And it's zero order if it's concentration versus time being linear, first order if it's the natural log of the concentration versus time being linear, and second order if it's the reciprocal of concentration versus time being linear.